More than 14 billion miles from where you're sitting right now, a spacecraft launched before most of your parents were born just sent back a signal that has researchers genuinely stumped. Not stumped in the exaggerated headline sense, stumped in the sense that the data doesn't match any model anyone has built, and nobody currently has a clean explanation for what's actually going on out there. Stick around, because I'm going to walk you through exactly what Voyager 1 detected, why scientists didn't expect it, and why this tiny ancient spacecraft keeps rewriting what we thought we understood about the edge of our own solar system. If you want more of these deep dives into real published research instead of recycled headlines, go ahead and subscribe now, because there's a lot more coming out of the darkest corners of our solar neighborhood. To understand why this matters, you have to understand just how far past the edge of everything familiar Voyager 1 actually is. It launched in September of 1977, originally built for a mission that was only ever supposed to last about 5 years, flying past Jupiter and Saturn to send back the first truly detailed images of those planets and their moons. It did that job so well that NASA kept extending its mission again and again for decades. By August of 2012, after 35 years of continuous flight, Voyager 1 crossed a boundary called the heliopause, the invisible edge where the constant outward stream of charged particles from our sun, known as the solar wind, finally gets overpowered by the thin gas and plasma that fills the space between stars. Crossing that boundary made Voyager 1 the first human-made object in history to leave the bubble of our solar system entirely and enter true interstellar space. It is, right now, the single most distant piece of human engineering that has ever existed, and it is still talking to us, still sending back data more than 4 decades after launch. Here's what makes that almost hard to comprehend. A radio signal from Voyager 1, traveling at the speed of light, takes over 22 hours to reach Earth. When engineers send a command up to the spacecraft, they then have to wait nearly 2 full days just to find out whether it worked. The spacecraft runs on a radioactive power source called a radioisotope thermoelectric generator, which converts the heat from decaying plutonium into electricity. That power source loses a small amount of output every single year, with no way to refuel it or replace it ever for the rest of the mission's existence. As a direct result, mission engineers have had to make increasingly difficult choices over the decades, shutting down individual heaters, cameras, and scientific instruments one by one, prioritizing whichever systems still give researchers the most valuable data per watt of remaining power. The onboard cameras were switched off decades ago, not because they broke, but because keeping them powered was no longer worth the electricity it cost. What's left running today is a stripped-down core of instruments, just enough to keep measuring the environment around the spacecraft and just enough to keep talking to Earth. And yet, against every reasonable expectation, this half-century-old machine keeps finding things that genuinely surprise the scientists monitoring it. It helps to understand just how differently this mission was originally planned. When Voyager 1 and its twin, Voyager 2, launched within weeks of each other in 1977, NASA's primary goal was a close study of Jupiter and Saturn, taking advantage of a rare planetary alignment that let the spacecraft use each planet's gravity to slingshot toward the next target without burning through decades of fuel. Nobody involved in the original mission design was under any illusion that these spacecraft would still be functioning, let alone making genuinely new discoveries nearly 50 years later. Every extension beyond that original planetary tour, including the eventual push toward and through the heliopause, has been treated internally at NASA as bonus science, squeezed out of hardware that has long since outlived every reasonable estimate of its working lifespan. The most recent puzzle centers on Voyager 1's magnetometer, the instrument that measures the strength and direction of magnetic fields around the spacecraft. Starting in early 2021 and continuing into 2022, researchers noticed something in the data that hadn't shown up before, a prolonged, unusually sustained increase in the strength of the interstellar magnetic field surrounding the spacecraft. Scientists have since nicknamed this stretch of data the magnetic hump. What makes it strange isn't just that the field got stronger. Voyager 1 has recorded temporary spikes in magnetic field strength before, usually tied to shockwaves rippling outward from solar storms back near our sun. Those spikes come, peak, and fade. This one didn't behave that way. The elevated field strength lingered for roughly a year, and according to researchers who have continued tracking the data through 2025, the field has never fully returned to the levels recorded before the hump began. Something changed out there in a way that doesn't cleanly match the shockwave pattern researchers had come to expect. If you're finding this as strange as I did while researching it, drop a comment and let me know, because it genuinely helps me figure out what other space stories are worth covering next. To understand why a lingering magnetic anomaly is such a big deal, you need to understand what scientists actually expected to happen once Voyager 1 crossed into interstellar space in the first place. Before 2012, most researchers assumed that the direction of the interstellar magnetic field, once Voyager finally reached it, would look meaningfully different from the magnetic field inside our own solar system, since the two regions are shaped by completely different sources. Instead, when Voyager 1 actually crossed the boundary, the magnetic field's overall direction barely changed at all, even though the density of charged particles around the spacecraft jumped dramatically, roughly 40 times higher than what Voyager had been measuring just inside the heliopause. That mismatch confused researchers for years. If Voyager had truly left the Sun's zone of influence entirely, why did the magnetic field orientation look so similar to what it had been measuring before the crossing? A study led by researcher Nathan Schwadron at the University of New Hampshire eventually offered a partial explanation, proposing that the interstellar magnetic field lines were being dragged and draped around the outside of our solar system's heliopause, bent by the pressure of the heliosphere pushing outward from within, similar to how water bends and drapes around a rock sitting in a stream. Under that model, Voyager 1 would need to travel much farther, potentially another decade or more before it reached a region of truly undisturbed interstellar magnetic field, far enough from our solar system's influence that the draping effect no longer applied. That explanation helped make sense of the original mismatch. But the magnetic hump detected starting in 2021 doesn't fit neatly into that draping model either, and researchers are still working out whether it represents a completely separate phenomenon, a disturbance rippling in from somewhere else in the galaxy, or evidence that the boundary between our solar system's influence and true untouched interstellar space is far messier and more dynamic than the smooth, static picture scientists had been assuming for years. There's a second piece of this mystery that ties directly into the first, and it involves something almost nobody expected Voyager's aging instruments to be capable of detecting at all. Back in 2017, scientists analyzing archived data from Voyager 1's plasma wave instrument, the same equipment originally designed to detect sudden bursts of activity from solar shock waves slamming into the interstellar medium, noticed something in between those bursts. A faint, steady, almost musical hum, a continuous low-level vibration in the plasma surrounding the spacecraft that had nothing to do with any solar event at all. Led by Cornell University astronomer Stella Koch-Ocker, the research team spent years confirming that this wasn't noise or instrument error. It was a genuine persistent signal, the plasma equivalent of a constant quiet drone running in the background of interstellar space itself. Their findings were published in the journal Nature Astronomy in 2021. What makes the hum scientifically valuable is that its frequency reveals the density of the plasma around the spacecraft, essentially letting researchers measure how tightly packed the charged particles are in that region of space without needing any dramatic solar event to stir things up and make the measurement possible. Before this discovery, scientists could only measure interstellar plasma density during those rare, dramatic moments when a shockwave from our own sun happened to sweep past the spacecraft, events that occur unpredictably and only a handful of times over the course of years. The steady hum changed that completely, giving researchers a continuous, ongoing method of tracking plasma density rather than waiting for occasional, unpredictable bursts of solar activity to create a usable signal. Senior researcher James Cordes of Cornell described the ordinary background signal as something like a gentle, continuous rain compared to the loud, sudden thunderclap of a solar-driven shockwave passing through. But the mere existence of that steady hum raised its own question that nobody had fully answered before. If interstellar plasma is quietly vibrating on its own, independent of anything happening back near our sun, what exactly is sustaining that vibration over such a long, continuous stretch of time, across a region of space scientists had largely assumed would be closer to silent? Some researchers have proposed that low-level turbulence within the interstellar medium itself, unrelated to our solar system entirely, could be enough to sustain the signal, but confirming that would require exactly the kind of long-term, continuous monitoring that only a spacecraft already sitting out there, like Voyager 1, is currently positioned to provide. In the spring of 2022, engineers at NASA's Jet Propulsion Laboratory noticed something that shouldn't have been possible. Voyager 1, the most distant human-made object in existence, launched in 1977, and by then already deep into interstellar space, was behaving perfectly normal in every way that actually mattered. It was receiving commands from Earth and executing them correctly. It was collecting scientific data and sending that data back across billions of kilometers with no apparent problem. But one specific system on board, the attitude articulation and control system, the mechanism responsible for keeping the spacecraft's antenna pointed precisely at Earth, was sending back telemetry readouts that made no sense. The numbers coming down didn't match what the spacecraft was actually doing. It was, in the words of the engineering team at the time, a genuine mystery, a case where the patient seemed perfectly healthy, but one specific diagnostic reading looked like it belonged to a different machine entirely. And this wasn't a minor curiosity. Voyager 1 was, by that point, more than 20 billion kilometers from Earth. A radio signal sent from the spacecraft takes over 20 hours just to arrive. Diagnosing and fixing a problem on a computer that far away, built with 1970s technology, using documentation that, in some cases, existed only on paper in filing cabinets because the engineers who designed the original systems had long since retired, is about as close as modern engineering gets to defusing a bomb over a phone call with someone speaking a language nobody remembers fluently anymore. That first anomaly turned out to be a genuinely elegant piece of detective work once the team traced it down. The AACS wasn't malfunctioning. It was still doing its job correctly, actively controlling the spacecraft and keeping the antenna locked onto Earth exactly as it should have been. What had gone wrong was narrower and stranger than that. The telemetry data specifically, the readout meant to report on the AACS's own status back to mission control, was being routed through a different piece of onboard hardware than intended, one that had apparently stopped functioning correctly at some earlier point without anyone noticing, because nothing depended on it in a way that had caused a visible problem before. The spacecraft's actual behavior was fine. Its ability to accurately report on its own internal state through that one specific data channel was broken. It's the equivalent of a person being in perfectly good health, while one specific gauge on a hospital monitor hooked up to them is quietly reading numbers pulled from an entirely different, disconnected sensor. Once engineers understood that distinction, they were able to work around it, rerouting the telemetry reporting through a different onboard system and confirming that Voyager 1's actual. Operations had never been at risk, it was resolved, it was fully explained, and it demonstrated something that would matter enormously 18 months later, that this specific spacecraft, at this specific stage of its life, 45 years into a mission originally planned to last 4, was capable of producing anomalies odd enough to genuinely puzzle its own engineering team, without any of it meaning the mission itself was in danger. The far more serious anomaly began in November 2023, and this is the one that actually deserves the word mystery. Voyager 1 suddenly began transmitting something that looked, to the engineers receiving it, like gibberish. Not silence, and not a weakened signal, which would have suggested a simple loss of power or a misaligned antenna. The radio carrier wave itself was arriving exactly as expected, strong and steady, which told engineers the spacecraft was alive, powered, and still correctly pointed at Earth. But the actual data riding on that signal, the structured stream of ones and zeros, meant to carry both scientific readings and engineering health reports back to mission control, had turned into a repeating, meaningless pattern. For 5 months, this continued. NASA's engineering team, some of whom were brought back specifically because of their decades-old familiarity with a spacecraft computer architecture that predates most currently employed engineers' careers, worked to trace the fault, a task made almost absurdly difficult by the communication delay alone. Every single command sent to the spacecraft to test a theory took roughly 22.5 hours to arrive, and then another 22.5 hours for any response to come back. A single round of troubleshooting, one test, and one result took the better part of 2 days, every time, with no room for a quick follow-up question the way you'd have with literally any other computer on Earth. What the team eventually traced the problem to was refreshingly, almost anticlimactically mundane once they found it, and that's exactly what makes it a genuinely satisfying story rather than an unresolved one. The fault lived inside the flight data system, the onboard computer responsible for packaging Voyager's science and engineering data before it gets handed off to the radio transmitter. A single corrupted chip inside that system, likely degraded after decades of exposure to the radiation environment of deep space, had started producing garbled output. Engineers worked out a way to route the affected function around the damaged chip entirely, reprogramming the spacecraft's memory to bypass the faulty section, a repair performed on 46-year-old hardware, sent as a set of remote commands across a communication delay of nearly a full day each way, on a machine with roughly 69 kilobytes of memory total, less computing power than a single modern greeting card that plays a tune when you open it. By the spring of 2024, Voyager 1 was sending back clear, readable data again. The mystery had a real, complete, thoroughly boring, in the best possible sense, explanation. A worn-out chip on an antique computer, fixed by patient engineers willing to write software patches for a machine most of them weren't alive to see launched. The third event is the one that most directly explains why Voyager spotted something scientists can't explain. Headlines have been circulating recently, and it's also the one that shows most clearly how a completely ordinary event can get inflated into something that sounds like first contact. In November 2025, reports began spreading online describing a faint, unexplained signal detected in connection with Voyager 1, quickly nicknamed in various headlines as a ghostly transmission from deep space. For a brief period, public speculation genuinely ran toward the idea that something unexpected, possibly non-human, had been picked up near the probe. The actual explanation, once space agencies clarified it, turned out to be almost charming. The signal wasn't coming from Voyager 1 at all, and it wasn't unexplained in any technical sense once someone checked the schedule. It was a planned transmission from the European Space Agency's Deep Space Antenna Facility in Chebarros, Spain, a live radio broadcast of the Vienna Symphony Orchestra, performing Johann Strauss II's The Blue Danube, sent out into space as a piece of scheduled science communication and cultural outreach using the same deep space antenna infrastructure that tracks missions like Voyager. Because the transmission happened to be associated with that same network of antennas used to communicate with the most famous spacecraft in history, and because initial public reporting was vague about the source, the story mutated within days into a viral, mysterious signal near Voyager headline. And from there, into an even more exaggerated wave of blog posts inventing details that never happened at all, quantum processors, recursive symbolic patterns, non-human structure buried in the telemetry, none of which appear anywhere in NASA or ESA's actual technical communications. It's a near-perfect case study in how an entirely explainable publicly scheduled event, a symphony orchestra broadcast, can get reframed within a single news cycle into something that sounds like a UFO encounter, simply because it happened in the same general context as a spacecraft people already associate with mystery and wonder. There's a reason Voyager keeps generating this kind of speculation more than any other spacecraft. And it's worth understanding, because it isn't really about aliens at all. It's about the genuinely strange, genuinely emotional position this particular machine occupies. Voyager 1 is not just old, it is currently more than 25 billion kilometers from Earth. They're deep enough into interstellar space that it has fully left the region of space still under the direct influence of the sun's solar wind. Signals to and from it take nearly a full day to make a one-way trip. It's operating on decades-old technology, kept alive by a small, aging team of engineers who understand its systems well enough to write patches for a computer built before most of them were born, using documentation that in places genuinely exists only on paper because it predates searchable digital archives. It also carries the golden record, a phonograph disc loaded with sounds, images, and greetings from Earth, assembled under the direction of Carl Sagan specifically for the improbable scenario that some other intelligence might someday intercept it. That combination, a machine that is both an aging, physically failing piece of hardware and a symbolic message in a bottle launched into the cosmic ocean, makes it uniquely primed for exactly this kind of story. When something goes wrong with Voyager, and after nearly 50 years in the harshest environment humans have ever sent a machine into. Of course, things periodically go wrong. The emotional weight already loaded onto the spacecraft makes it almost irresistible to reach for the most dramatic possible explanation rather than the real one. Even when the real one, patient engineers rewriting data around a dying chip using a computer with less memory than a digital watch, 46 years after launch, is honestly the more impressive story. What the last few years of real Voyager anomalies actually show, when you follow them all the way to their true, documented conclusions, is not evidence of anything unexplained lurking at the edge of the solar system. It's evidence of just how remarkable it is that this specific machine is still working at all, and just how good the small team responsible for it has gotten at keeping something built in the disco era alive and useful decades, past its original mission plan, using nothing but patience, decades-old documentation, and the willingness to wait 2 full days for a single line of code to travel out, execute, and report back whether it worked. Voyager 1 has now been operating for approaching 50 years. Its plutonium power source loses a small amount of output every year, and NASA has been carefully, deliberately shutting down individual instruments, one at a time over the past several years, specifically to stretch the spacecraft's dwindling power supply and keep at least some of it transmitting for as long as physically possible, likely into the early 2030s, before it finally goes silent for good. Every anomaly it produces between now and then is going to be genuinely interesting, because a machine this old, this far away, and this thoroughly outside the reach of any repair crew generating strange telemetry readings is not a mystery that needs an exotic explanation. It's exactly what you'd expect from the oldest, farthest, most quietly heroic piece of engineering humanity has ever built, still doing its job, still occasionally confusing the people back home, and still, every single time so far, turning out to have an answer that is grounded, findable, and human. Then came a separate and equally puzzling discovery. As Voyager 1 continued drifting deeper into interstellar space through the 2010s, researchers noticed the plasma density around the spacecraft wasn't staying constant. It was slowly climbing, becoming denser the farther Voyager traveled from the heliopause. That, on its own, might have been dismissed as some kind of local fluke, a single unusual patch of denser gas that Voyager 1 simply happened to be passing through. Except in November of 2018, Voyager 1's twin spacecraft, Voyager 2, crossed its own boundary into interstellar space at a completely different location on the opposite side of our solar system. And Voyager 2 detected the exact same pattern. A gradual, steady increase in plasma density the farther it traveled from the heliopause. Two separate spacecraft, launched decades ago, moving in almost entirely different directions, both measuring the same unexpected density gradient. That kind of agreement between two independent instruments moving through two different regions of space made it extremely difficult to write the finding off as a coincidence or a local anomaly. Researchers now suspect the increase may reflect a genuinely large-scale feature of the interstellar medium surrounding our solar system, though there's still no fully confirmed explanation for exactly why the density behaves this way. One leading idea involves the same magnetic draping effect that helps explain the field direction mismatch. As interstellar magnetic field lines wrap and compress around the outside of our heliosphere, the theory goes that compression could trigger a kind of plasma instability, one that gradually strips charged particles away from the draped region and effectively piles up extra density farther out in the direction Voyager is heading. Another proposed explanation points to the physics of the interstellar wind itself, the idea being that material blown through that region of the galaxy naturally slows down as it approaches the outer edge of our heliosphere, creating something like a traffic jam of particles that builds up density over time. There's even some indirect supporting evidence for that second idea. In 2018, the New Horizons spacecraft, the same probe that gave scientists their first close look at Pluto, picked up a faint ultraviolet glow consistent with a buildup of neutral hydrogen piling up right at the boundary of the heliopause, which would fit reasonably well with the traffic jam explanation. But neither idea has been confirmed outright, and researchers studying the newer magnetic hump data through 2025 note that the picture keeps getting more complicated rather than settling into a single clean answer. It's worth pausing here to explain why any of this actually matters beyond simple curiosity. The boundary between our solar system and interstellar space isn't just some abstract line on a diagram. It's the region that determines how much of the sun's radiation and charged particles reach out into the wider galaxy, and in turn how much cosmic radiation from other stars manages to reach us. Understanding exactly how that boundary behaves, whether it's a smooth, gradually changing transition or something far more turbulent and dynamic, has real implications for how scientists model the safety of future deep space missions, how they interpret radiation exposure for anything traveling beyond our solar system, and even how they understand the broader structure of the galaxy immediately surrounding our own sun. A boundary that behaves unpredictably, with lingering magnetic disturbances and unexplained density gradients, is a very different scientific picture than the neat, static edge many models assumed decades ago, back before Voyager 1 ever actually got there to check. What makes all of this even stranger is the sheer unlikelihood that we're getting this data at all. Voyager 1's instruments were designed using technology from the 1970s, decades before anyone seriously expected the spacecraft to still be operational by the time it reached true interstellar space. Its onboard computer has less processing power than a basic pocket calculator you could buy today. NASA engineers have had to relearn old programming languages and dig up archived documentation just to keep issuing commands to a system built with technology that predates most modern computing entirely. Power is running low enough that mission engineers have been forced to shut down individual scientific instruments, one at a time, over the past several years, simply to keep the spacecraft's remaining systems alive long enough to keep transmitting. Every additional year of data Voyager 1 sends back at this point is, in a very real sense, borrowed time, and every one of those years has kept adding new pieces to a puzzle nobody expected the mission to still be solving this far past its original 5-year expiration date. There's also a broader context worth sitting with here. Voyager 1 and Voyager 2 remain, to this day, the only two spacecraft that have ever directly sampled interstellar space. Every other observation we have of that region, from every other observatory and every model built by every research team, is either theoretical or based on indirect measurements taken from safely inside our own solar system. The Voyagers are the only ground truth we have out there, the only actual on-site sensors reporting back from beyond the edge of everything the sun protects. When Voyager 1 detects something that doesn't match the model, there's no second instrument sitting right next to it in interstellar space to double-check the reading. Researchers have to work with exactly what a single 48-year-old spacecraft sends back, sometimes only a handful of readings at a time due to power constraints, and piece together the broader picture from there. That's part of why findings like the magnetic hump generate so much genuine scientific interest rather than dismissal. It isn't that scientists doubt the data. The instruments have proven remarkably reliable over the decades, and the readings have been cross-checked repeatedly against everything else Voyager 1 has recorded since 2012. The issue is that the data simply doesn't fit comfortably into the models researchers had built to describe how this boundary region should behave. And when observational data consistently outruns the models, meant to explain it, that's usually the exact moment where genuinely new physics tends to get uncovered. not through some dramatic breakthrough moment, but through years of careful, incremental analysis of unusual readings just like this one. It's also worth noting how unusual it is for a single instrument to keep contributing new, peer-reviewed findings across such an enormous span of time. Most scientific instruments are designed, built, used intensively for a relatively short operational window, and then retired once newer technology replaces them. Voyager 1's magnetometer and plasma wave instruments have instead been quietly gathering data for close to 5 decades straight, across conditions absolutely nobody anticipated when the hardware was first assembled. Researchers analyzing this most recent stretch of data, covering the magnetic hump and its lingering aftermath through 2025, are essentially working with the longest continuous dataset humanity has ever collected, from beyond the edge of its own solar system, which is part of why every new anomaly carries so much weight. There's no comparable archive anywhere else to check it against. NASA has no current plans to send another spacecraft to directly sample interstellar space anytime soon. A mission capable of reaching that same boundary would take decades of travel time at minimum, using anything close to current propulsion technology, and outer solar system missions have historically struggled to receive consistent funding compared to projects with faster, more immediate scientific returns. There has been occasional discussion within the scientific community of a dedicated interstellar probe mission, purpose-built with modern instruments and a faster trajectory than either Voyager achieved, but any such mission remains firmly in the conceptual and proposal stage without confirmed funding or a set launch date. For the foreseeable future, Voyager 1 and its aging twin remain humanity's only working outposts in that region of space, our only real-time witnesses to whatever is actually happening out past the edge of the sun's influence. It's a strange thing to sit with, the idea that our clearest window into the space beyond our own solar system still runs on hardware from the disco era, patched together by engineers who have had to become historians of their own agency's old programming manuals just to keep the lights on. So what does all of this actually add up to? A spacecraft designed in the early 1970s, running on technology that predates the modern smartphone by half a century, just handed scientists a magnetic anomaly that has lingered for years without a clean explanation, layered on top of an unexplained density gradient confirmed by 2 separate spacecraft, layered on top of a persistent plasma hum that nobody expected to find at all. Nearly 50 years after launch, Voyager 1 is still teaching us that the edge of our solar system is a far stranger, far more dynamic place than anyone modeling it from a comfortable distance ever assumed. If stories like this one, grounded in real published research rather than exaggerated headlines, are what you want more of, subscribe to this channel and turn on notifications, because Voyager is still out there, still transmitting, and there's a real chance the next signal it sends back adds another genuinely strange piece to this puzzle. Thanks for watching, and I'll see you in the next one.